रेल में जो फटीग फेल्यूर है, एक तो आपका जो RCF, दैट इज रोलिंग कॉन्टैक्ट फटीग. It is basically in the head portion due to very heavy contact stresses and high shear stresses, like जिससे आपका जो कि रेल में शेलिंग होती है और आपका जो किडनी फ्लो डेवलप होता है, right? And as we discussed just now, it is unavoidable to have this because you cannot have the rail strength where the contact stresses can be less than the strength of the rail. It's not possible to have that kind of rail. So RCF is part and parcel of our life. It has to be there. Rolling contact fatigue failures have to be there. Only thing they can be controlled by rail grinding, right? That's why for higher axle loads, rail grinding is must. If we are going for 25 ton axle load and if we don't deploy the rail grinding, our rails will fail at very low GMT. जिससे अभी हम 800 GMT की उम्मीद करते हैं, प्रोबेबली वो 300, 400, 500 GMT पे भी 60 kg रेल फेल हो जाएगी विदाउट रेल ग्राइंडिंग. ओके, एंड विथ रेल ग्राइंडिंग इवन जो अभी 800 GMT की हम बात करते हैं, दैट लाइफ कैन बी एनहांस्ड अप टू मे बी 200 और 1200 GMT also. So rail grinding has tremendous advantages and Indian Railways is going to adopt this rail grinding on a very massive scale. Lot of machines are under pipeline, they are being procured. Okay. Other fatigue failure is due to bending. So bending fatigue failure can be controlled or bending fatigue failure can be avoided by designing the rail in such a way that that endurance limit or the fatigue strength of the rail does not get exceeded. Okay, so let us discuss about this. So when rail is subjected to cyclic loading, it is likely to fail. It is likely to fail at a stress level of lower than its yield strength, right? जो आपकी yield strength है उससे कम पे भी फेल हो जाएगी अगर कोई भी मटेरियल subjected to cyclic loading when subjected to a finite number of loading cycles, right? So however, if stress is less than certain value called the endurance limit, this is also known as fatigue strength, rail can withstand infinite number of loadings, right? Basically what we are trying to tell is that if you subject the rail to cyclic loading but the stress level is lower than the endurance limit, then rail can sustain infinite cycles of such loading, right? जो कल थोड़ा सा मैंने आपको बताया था, ये बेसिकली इसकी जो एनालिसिस है वो एक SN कर्व ड्रॉ करके की जाती है. Here S is stress and is number of cycles up to failure, right? And steel के लिए SN curve is something like this, right? There is one dropping curve up to this point, right? So if I take the yield level as the failure level and this will be my yield level, right? It means what? If I apply the stress up to yield level, then my rail will fail in the one cycle itself, or material will fail in one cycle itself, right? So here this is your basically stress, and on the horizontal this is N, which is number of cycles of loading. Okay, if I take this point, right, then if I apply this reversible stress up to this level, say sigma 1, right, then corresponding number of cycles N1 will be the life of this rail here, right? So it can sustain N1 cycles of loading which generate sigma 1 reversible stress, right? If I take this point, right, then this is basically say N2 cycles and this is my stress level sigma 2. So if I apply sigma 2 reversible stress, then this rail can take N2 cycles. If my stress level is less than sigma 2, right, if it is less than sigma 2, it means it's less than your endurance limit, then this material will never fail due to this cyclic loading. So this is basically the concept of fatigue in the materials. Okay, so this kind of concept is applicable to rail also, right? ये जो एसन कर्व ड्रॉ किया जाता है उसका थोड़ा लोडिंग का भी मैं आपको एक्सप्लेन कर देता हूं, हाउ दैट लोडिंग इज टेकन, हाउ दैट रिवर्सिबल लोडिंग. तो रिवर्सिबल लोडिंग विल बी बेसिकली, it is completely reversible loading. It is giving compression and tension equally, right? So this is your average stress is 0 here, right? This is your maybe tensile stress, this is your compressive stress, both are equal. So this is fully reversible loading. But normally in practical situations this kind of loading may not be available, right? Based on this fully reversible loading, we calculate what is the endurance limit for that material. So endurance limit and that SN curve is drawn based on this kind of experiment, right? But in actual situation, the situation is slightly different. So what is that? Let me try to explain that. In actual situation, the loading cycle might be something like this, right? And your datum might be here, right? So maybe you have higher tensile stresses but lower compressive stresses. Okay, so your material might be undergoing this range, okay, and it will have the mean stress somewhere here. This will be the sigma mean, right? A rail is subjected to this kind of loading. So for this kind of loading, the endurance limit straightway will not be applicable, right? Then there is something, some analysis has been done and some people have drawn some graphs. One is Mr. Smith. There is one Mr. Smith who has drawn some graphs. Through those graphs, we can calculate for a certain value of endurance limit. For example, for our rail, the endurance limit is 330 MPa. तो अगर 330 MPa हमारा endurance limit है, and my उस endurance limit के लिए what will be the applicable range of sigma T to means tensile stress to compressive stress. This kind of range has to be calculated, right? So that range is calculated for our rail also. I am going to talk about that in a short while. Okay. These are basically, I cannot discuss these things in detail because this is about the fatigue phenomena and that takes a lot of time to discuss everything in that. I just explained you the basic concepts. Okay. Now this endurance limit or the fatigue strength of our rail is measured by Belay. They have done some experiments. RDCIS is one laboratory under the Ministry of Steel, under basically SAIL. It is located in Ranchi, and they have calculated the endurance limit for our rail, which is 90 UTS rail, right? Conventional 90 UTS, not R260. For that, the endurance limit is 333 MPa. मतलब क्या है इसका कि अगर fully reversible load हो, right? So ये जो limit है ये 330 MPa है पॉजिटिव साइड में एज वेल एज माइनस साइड में. तो इस लेवल का स्ट्रेस अगर लग रहा है रेल पे तो ये रेल कभी फेल नहीं होगी. व्हाट इज द यील्ड स्ट्रेंथ? यील्ड स्ट्रेंथ हमारी 460 है, राइट? सो इसका मतलब क्या हुआ? इफ इट इज से सब्जेक्टेड टू 375 MPa, even though the 375 MPa is less than yield strength, but this material will fail after certain number of cycles. Those cycles will be in the millions. Okay, this is the basic thing about this. Okay, so but now our rail is subjected to the constant stress that I told you. Constant stress such as residual stress, thermal stress, and some other kind of stress, right? Such as those who flex laying of rails on curves. So our rail not only subjected to the cyclic loading, it is subjected to the constant stress also. So our loading is not fully reversible, right? It will have more value towards tensile stresses, less value towards compression stress, especially at the critical location, which is the foot center in our rail. Okay. And for 60 kg rail in temperature zone 4, we have calculated that temperature stress is 11.32 kg per millimeter square. Residual stress is 24.5 per millimeter square. Right? Thus, the total constant stress at rail foot center, this is the critical location for our rail, is worked out as 36.82 kilogram per. So this is sort of a constant stress. Here, constant does not mean like always this is the stress, because temperature stress will not be available always, but it is available for a longer duration as compared to the wheel loads. So we take this as the constant stress. Okay, so it's the 36.82 kg per millimeter square. Now the maximum and minimum bending stress, this is due to wheel load. At rail foot center for 60 kg rail under 25 ton axle load at 100 kmph. So these are the some values. Maximum 13.76 kg per millimeter square, minimum 3.07 kg per millimeter square, that is compression, and this is tension. So at rail foot center, the bending stress due to wheel load varies between these two limits. Okay, so this is also not a fully reversible stress. It would have been fully reversible if the compression stress also was minus 13.6. So it's not a fully reversible stress. So for this, the endurance limit cannot be taken directly, right? So we have to use the Smith diagram for that. Now these are the maximum and minimum and mean stress. Now we have to calculate what is the maximum stress, what is the minimum stress, and what is the mean stress to which rail is subjected again at the rail foot center, right? Combined maximum stress ये आपका residual, thermal, and then this stress due to bending. ये इतना हो गया. And combined minimum stress, residual, thermal, and then this bending. ये हो गया. So basically our rail is subjected to this kind of range, right? This is basically 32.75 kg per millimeter square to 49.58 kg per millimeter square, right? And both rails, both stresses are tensile. So mean stress 41.16. Now for these things, this is maximum stress and minimum stress and mean stress. We have to work out what is the range in which our rail stresses or what is the permissible range. We have to work out the permissible range for the mean stress as well as for endurance limit. तो वो जो permissible working range है, right, from Smith diagram, वो हमारी 46.8 kg to 30.5 kg per meter square आती है, as against the required range. Required range previous page पर अपने workout की थी 49.58, 32.75. So this is my required range, right, for infinite life, right? But permissible range ये है, right? But मुझे required इतनी चाहिए थी. इसका मतलब permissible is less than my required range. So I will not have the infinite life as far as bending fatigue is concerned. Okay, I am not going to get the infinite life for this rail. But getting infinite life in the bending strength is really not important. What is important is the life due to bending should not be less than the life of the rail due to other considerations. What are other considerations? One is RCF, rolling contact fatigue, and then another is wear, right? So if I worry too much that I want to get the infinite life due to this bending fatigue failure, then there is no point in that, because my rail is ultimately going to fail either due to RCF or I am going to replace the rail on wear account, right? So what should be your requirement is that the life under this bending fatigue should be more than the life under RCF or wear, right? So my rail should not be required to be replaced due to bending fatigue, right? In any case, the rail will be required either due to RCF failure or due to excessive wear. So this is the whole theory according to which the rail design is done, and by calculating the rail stresses and by calculating these permissible ranges. Okay. So, any queries on this? Okay. Now, what is the future planning for Indian Railways? What is the current status? Current status is that we are using 98 UTS rails. From that, we have gone to this is 90 UTS. We can call it conventional rails, right? We have gone to R260. R260 is also 90 UTS, but with better yield strength, right? Here, the yield strength was 52% of UTS. Here it is around 62% of UTS. So by slightly changing the chemical composition and by better rolling process or manufacturing process, we are able to improve the yield strength. So our rail, as far as yield strength is concerned, has become safe even for 25-ton loading. But still this R260 rail is found wanting when we calculate the contact shear stresses, right? So the next step is that we have to go for 110 UTS rail, right? And this has been suggested for 22.9 ton and 25-ton axle load. So this is going to be a universal rail. But when we use higher strength rail, they become more brittle. They become more susceptible for the fractures. Okay, so it's not something like we are getting only benefit. So we cannot increase the UTS indiscriminately because it is going to make the rails more brittle. Right? So there is a trade-off between this. But of course, from shear stress consideration, there is no option but to go for 110 UTS rails. Right? And when we go for 110 UTS rails, and when we operate 25-ton axle load, then grinding is inevitable. Right? Grinding has to be there. See, what is one more disadvantage of higher UTS rails? हायर यूटीएस रेल जैसे ही आप अडॉप्ट करोगे तो जो सरफेस वियर है रेल का, रेल टॉप पे और रेल हेड में जो वियर है उसकी रेट कम हो जाती है, और सरफेस में जो अगर वियर की रेट कम हो जाती है तो जो सरफेस डिफेक्ट जनरेट होते हैं रेल में, राइट, उनको ग्रो करने का टाइम मिलता है. अदरवाइज क्या होता है, जब रेल में वियर होता है तो वियर से नुकसान नहीं है, वियर से एडवांटेज भी है. एडवांटेज ये है जो सरफेस डिफेक्ट जनरेट होते हैं, सरफेस क्रैक जनरेट होते हैं, वो वियर के कारण निकलते रहते हैं. इसीलिए हमारी जो 72 यूटीएस रेल होती थी उसमें किडनी फ्लॉ या शेलिंग काइंड ऑफ प्रॉब्लम्स बहुत कम होती थी, होती नहीं थी. 90 यूटीएस रेल में बढ़ गई हैं. 110 यूटीएस में वो इश्यूज और बढ़ जाएंगे, किडनी फ्लॉ बढ़ जाएंगे, शेलिंग वाली जो प्रॉब्लम्स है वो बढ़ जाएंगी, बिकॉज इसका रेट ऑफ वियर कम होता है. राइट. सो ग्राइंडिंग क्या करता है? ग्राइंडिंग बेसिकली रेल को आर्टिफिशियली वियर क्रिएट करता है. राइट. वी grind out or we remove material from the rail top, right? So it is basically artificial wear on the rail, right? So grinding becomes important for higher UTS rails. Otherwise these rails will have more RCF failures, right? And in the interim measure that I explained, we have gone for this R260 rail, which has given us 55 or 550 MPa yield strength. UTS is same, 880, right? So this is the interim thing we have done, and some slight changes in the chemical composition has been done as compared to our normal rail. Minor changes here and there. I think main change in the manganese में change कुछ किया है. Okay. Now what are the rail options available on like international EABC? The national guidelines over European railways for rail grade selection on the mixed traffic lines with up to 22.5 ton axle load and up to 20 GMT annual load suggest R260 for alignment flatter than 700 meters. So हमारे यहाँ ऑलरेडी ये एक्सल लोड है rather more than this 22.9 and mixed traffic है, and GMT भी on most of our routes है more than 20 GMT. Right, but we are using a rail which is inferior to R260. On European standards, they are using a R260 rail for alignment flatter than 700 meters. So curves flatter than 700 meters. For curves sharper than 700 meter, they have a R350 ST rail. Basically, this is heat treated rail है. और यहाँ 260 R260 में 260 is basically is hardness, and here R350, 350 is hardness. Okay, so this rail for curves sharper than 700 meters. So these are the standards on European railways. हमारे जो अभी current standards हैं, even though our loading is higher, 22.9 tons, they are inferior to these standards. Okay, but of course now we have adopted R260, so we are at par with them.
R350, what is the UTS, sir?
R350, see R350 में भी इसको क्या किया, हेड हार्डनिंग करके सेम यूटीएस रख के इसकी हार्डनेस बढ़ा दी है. इट इज द सेम यूटीएस बट इसकी हार्डनेस बढ़ा दी है बाय हीट ट्रीटमेंट. राइट, हीट ट्रीटमेंट करके दो तरीके से हार्डनेस हम बढ़ा देते हैं. एक तो ये हेड अकेले का भी हम हार्डनेस बढ़ा सकते हैं, तो इसको हम बोलते हैं हेड हार्डन रेल्स. और वी कैन डू द हीट ट्रीटमेंट ऑफ द एंटायर रेल and increase the hardness of the entire rail. Right? Normally the process is कि आप हेड का हार्डनिंग करके, हेड का हीट ट्रीटमेंट करके हेड की जो हार्डनेस है वो बढ़ा दो. राइट, सो बेसिकली देखो कर्व में क्या होता है, शार्पर कर्व्स में द रेल्स बिकम्स ड्यू फॉर रिप्लेसमेंट ऑन अकाउंट ऑफ वियर. जैसे आपके यहाँ भी आपने देखा होगा, इफ यू हैव ए कर्व शार्पर देन मे बी 2 to 2.5 डिग्री से अगर शार्पर कर्व है तो उसमें 90 यूटीएस रेल की जो लाइफ है ना वो 400-450 GMT में पूरा उसको वियर हो जाता है. यू माइट हैव एक्सपीरियंस्ड दैट. Okay,
this 260 and 350.
Pardon me?
So this 260 and 350 are denoting the hardness number.
Yeah, that is hardness. That is Brinell's hardness number. Right?
Okay.
Right. Now we have some more issues in operation of heavier axle load on IR. What are the major issues? One is no means for measurement of forces at rail level. The dynamic and impact loading on track at various speeds not assessed. We have like those old graphs developed by RDSO in the 70s when the track structure was different, type of wagons were different, right? Axle load was different. But now the situation has changed completely. And best way to assess these things is to basically have the measuring wheel. So measuring wheel is going to be introduced in our system shortly. RDSO has already received that. Okay, and select criteria for acceptance. For example, dynamic load के लिए अभी हमारे यहाँ कोई upper limit नहीं है. Like UIC ने upper limit lay down की हुई है कि dynamic load cannot be more than 210 kilonewton. Right? Then no limits for acceleration values for freight stock. As per UIC, the freight stock cannot have maximum vertical acceleration more than 0.5 g and lateral acceleration 0.3 g. For our freight stock, these values are considerably higher. Right? So we have these issues because you can increase the rail strength and rail size, but unless you are going to control these things, our maintenance inputs are going to increase tremendously. Okay, so these are the issues that Indian Railways has to address. So this results in clearing of stocks having more adverse effect on track during operation. Then oscillation trials on new stocks only. हम जो oscillation trial करते हैं नए stock पे करते हैं, पर जब stock पुराना हो जाता है due to deterioration by use, then it will have more adverse effect, right? It will have more dynamic augment, it will have more acceleration. So basically we must do the oscillation trials on the old stock also. So that is not the practice on Indian Railways so far. Then the wagon having reduced wheel diameter. Right now we have reduced, I think on DFC they are going to run the trains with reduced wheel diameter for that double stack container and for increasing the load carrying capacity. Right? So if this is the containment limit, then it is going to increase the contact stresses, it is going to increase the shear stress in the head, so it is going to increase the RCF failures considerably. Right? So these are the issues. Then high value of acceleration of present heavy axle load wagons 0.6 to 0.87 g, जो कि 0.5 g maximum है for vertical and 0.3 g है maximum for lateral as per UIC. हमारे यहाँ जो wagons हैं उनका जो acceleration है it's pretty high, right? So it imposes more dynamic load on our track. Okay, so no track structure can sustain such high dynamic load and heavy vibrations. right? So these are the issues that Indian Railways is grappling with, and basically we have to issue, or we have to address these issues in the due course of time, right? Then UIC, there is one UIC leaflet 724-R, and this leaflet basically lays down what is the track equipment for 25-ton axle load on ballasted track. तो इसमें कुछ गाइडलाइंस ले डाउन की हुई हैं, right? International study and literature indicate that best way to decrease the deteriorating effects on track when operating with high axle load is through reduction in dynamic wheel loads, right? So, and reduction in dynamic wheel loads is basically through there are various options: good track geometry, good wheel quality, and track friendly vehicle design. So there is a limit to achieving the good track geometry, there is a limit to achieving the good wheel quality also. Main thing is basically to track friendly vehicle design so that it imposes less dynamic forces on the track, right? So this is the thing that we need to have. Unfortunately, our wagons fail on this criteria, right? So there is a lot to be done if we want to operate 25-ton axle load successfully and without excessive failures. So track friendly vehicle design becomes most important factor. Okay. On Indian Railways, we have issued certain guidelines for heavy haul running. Install all sanctioned weigh bridges and ensure that all weigh bridges are kept well maintained and functional. We are not ensuring this. No overloading must be permitted. Drastic penal action should be taken against defaulters. Better enginemanship and adequate powering should be ensured to prevent instances of stalling and wheel slippages. We are failing miserably in this also. Wagons must be well maintained. Additional springs as advised to provided during ROH or POH. Wild must be installed at all selected locations within 1 year. Not many wilds have been installed and probably they are not being maintained properly. All remaining instrumentation of bridges etc. should be concluded without any further delay. These instructions were issued way back in 2006 when we started running CC plus 2 plus 6 and then CC plus 8. Right? We have laid down so many guidelines, but unfortunately most of these guidelines have not been followed strictly. Anyway, so this was all about the rail stresses. We come to the end of this discussion. The basic idea is to give you some overview that track is subjected to certain kind of forces, right? Certain kind of stresses, and what is the relative importance of various stresses, which stresses we can control by improving the rail metallurgy, rail design, and which stresses need to be controlled during maintenance. For example, contact stresses, I cannot design probably the rail for the contact stresses, but I have to manage them during maintenance, that is to the rail grinding, etc. Right? So this topic of course may not be very relevant for the AENs, right? Basically at the senior level this becomes more relevant, but it's always good to have some knowledge about this topic. Okay, so I come to end of my talk. If you have any queries I can answer that, otherwise my time is